Hello, my name is Jordan Schalter, and welcome to my final project presentation for IT 559, Natural Language Processing in Practice. Today I'll be presenting my project titled Docstring-Aware Code Understanding using CodeSearchNet and Deep NLP Models. Throughout this presentation, I'll be switching between my PowerPoint slides and my Juniper notebooks so that I can walk you through both the conceptual reasoning and the actual technical implementation of the NLP models. Let's begin. Project overview. The central goal of this project is to investigate how well NLP systems can understand software documentation, specifically docstrings, and use that understanding to perform two major tasks. Retrieve the correct function implementation using only the text of its docstring, and predict which programming language a docstring belongs to, such as Python, JavaScript, or Java. These tasks are critically important for modern development tools, including AI code assistants, code search engines, documentation automation, static and dynamic program analysis, developer productivity tooling, and then we're going to switch over to this notebook cell one. In notebook cell one, that's where I handle my environment setup. Here, the notebook initializes all the required Python and NLP libraries. GPU detection for acceleration, reproducible random seeds, and environment validation checks. This cell ensures that all experimental results from TF-IDF baselines to Distilbert fine-tuning are completely replicatable, which is essential to academic integrity and research quality experimentation. On to the next slide. In slide 3, we go over the problem definition and motivation. The project is guided by 3 core research questions. How well can character-level TF-IDF retrieve the correct code function from the dataset? Between the classical models and deep transformers, which is more accurate for docstring to language classification? And do docstrings behave like natural language? And can we meaningfully apply NLP analysis such as NER, QA, summarization, and Zipf's law? These questions help define both the methodology and the evaluation criteria for the project. Slide 4. CodeSearchNet dataset. For this project, I used a balanced subset of the CodeSearchNet dataset consisting of 2,500 Python samples, 2,000 Java samples, 2,000 JavaScript samples. Each sample includes a docstring, a function body, a language label. This dataset is ideal because it contains both natural language descriptions and executable source code. This enables combined retrieval and classification experiments. Cell 2, dataset loading. In this cell, the notebook attempts to load CodeSearchNet directly from Hugging Face. If the system is offline, it automatically falls back to the local JSNL dataset included with the project. This two-path loading design ensures reproducibility, portability, reliability in restricted environments, and it also demonstrates one of the core engineering principles emphasized in IT 559, robust data acquisition pipelines. And here we're just running the cell. And there's our output. Slide 5, Preprocessing Pipeline. Before modeling, both docstrings and code undergo an extensive preprocessing pipeline. Docstring cleaning includes lower casting, regex normalization, stop word removal, lematization, I can never say that word, advanced token cleaning, that's from Lab 1. Code cleaning includes removing comments and strings, tokenizing using pigment lexers, normalizing identifiers, camel case, the small camel case, um, converting numbers to a num token, extracting semantic identifiers, and we'll handle this in cell 3 from the notebook. Here we produce language distribution bar plots, function length histograms, box plots by language, top token frequency tables, ZIPS law visualizations. ZIPS plots are particularly important because they confirm that docstrings behave like natural language, making NLP techniques appropriate and effective. Then we'll run it, and there's our bars. There's our output. Slide 6, the retrieval task. The first major modeling task is docstring to code retrieval. This requires placing docstrings code bodies into one shared TF-IDF character level feature space. This was a critical correction to earlier attempts where mismatched feature spaces prevented valid similarity comparisons. And we'll move on to cell 4 in the notebook. Cell 4, retrieval metrics. Here we compute cosine similarity, MRR at 10, recall at 10, precision at 10, NDCG at 10. These retrieval metrics are standard in information retrieval benchmarks. The results were MRR was 0.62, recall was 0.78, precision was 0.77, NDCG was 0.66. These were excellent results for non-deep learning model, highlighting how effective character level TF-IDF can be for code-related text. And we don't have to run it. And now we'll run. As you can see here, MRR at 10 is 0.6211034798534828, and recall at 10 was 0.7769230769230769. And there's our chart. Slide 7, model selection and training. For Docstring to language classification, we implemented multinomial Bayes, linear SVM, logistic regression, grid search CV tuned linear SVM. This aligns with deliverables 2 requirement to compare multiple model families. And we'll look at cells 5 in the notebook. And this cell applies word level TF IDF 1 to 2 n-grams, 80-20 train test split, classical classifier training, confusion matrix analysis, metrics table generation, best classical performance, tuned linear SVC to accuracy, 0.92 macro F1, macro F1 was 0.92. This showed that even without transformers, carefully tuned classical models remain extremely powerful for structured NLP tasks. And we'll run it. And there's our charts. Then we will move on to slide 8. Here's the previous slide. And in slide 8, we decide why Distilbert. Transformers provide semantic understanding, attention-based reasoning, transfer learning advantages, robust behavior on short text. Doc strings, while short, benefit from contextual understanding. That's something traditional bag of words methods cannot provide. We'll move on to cells 6 through 8. These cells include Hugging Face tokenization, Hugging Face dataset conversion, a manual PyTorch training loop, GPU acceleration via CUDA, validation and test evaluation, final Distilbert results. The accuracy was 0.913 and the macro F1 was 6.912. Dilbert performs slightly below the tune limit. Slide 9. Advanced NLP probing. Using Hugging Face pipelines, this section demonstrates NER over docstrings, summarization of long docstrings aggregates, question answering over code documentation, rogue metric evaluation, and these tasks show that docstrings behave similarly to human written text and can effectively be processed with general NLP models. And we will move forward over to cell 8 in the notebook. We've ran so make sure we ran cell 7 first. Yep, cell 7's run. This might take just 1 second. It should only take a second for this to finish running. And then we'll run cell 8. And then after that, we'll run all the rest of the cells. I'll just click run all below. Alright, now that the fine tuning is complete, we can go ahead and run cell 8, which is the Dilbert evaluation, metrics table, and inference helper. And there's our output. These results are really good. All 90s for precision, recall, and the F1 score. This is the matrix, and that's for our manual training loop. See, the accuracy is 91, 91, 89, 91, 91, 89. And then we save the weights and the tokenizers to the created by the notebook folder. So when you run this, it's going to create the notebook that's going to save the training to, which I also like to integrate in a lot of my programs that I write that leverage AI, because not only do you have the populated and saved data, but you could use this for like error logging, for example. I like to include a self-populated error log in some of my programs. It just makes it easier to debug. Anyways, enough about that. We'll move on to cell 9, which is the advanced text normalization with lemmatization. And this is the same output. A lot of this stuff is the same from Lab 1 deliverable and Lab 2 deliverable. I just integrated them into this final deliverable. I think it's cool to have it all in one spot. And so we'll run cell 10. That's the approximate zip curve for normalized docstrings. And then in cell 11 we have additional classical models and linear SVC hyperparameter tuning. That's from labs 3 and 4, I believe. Yep. And there's our output. And then cell 12, that's the extended retrieval metrics and qualitative error analysis. That's from lab 6. I did my best to integrate the labs into this final project, which I believe is what might set mine apart. I chose CodeSearchNet at the beginning and stuck with it instead of using different data sets for this reason. And we'll run the nurse, summarization, QA, and rogue integration. And then this is going to set to CUDA because GPU runs way faster. I went the first whole half of the semester without running off of my GPU because I couldn't get it to work. The NVIDIA drivers weren't up to date, and it was fast on the CPU and with the amount of RAM I have, but GPU is just way much better. So what this does is it asks the question, what does this code base generally do? Answer, values should be NP. That's because I didn't run, and this is why I said we're going to run all from the beginning. I initially recorded this presentation and realized that my headset was dead, so I had to go back and re-record it. So I'm going to go ahead, click all cells, and we'll continue to this point once they're ran. So as you can see, they're done running. The mapping is done, and we're on to cell 21. Dilbert fine-tuning with the manual loop and test set evaluation. These experiments provide qualitative insight into the structure, clarity, and complexity of documentation across different languages. So, we move on to combined metrics and interpretation. This is the retrieval metrics visualization. As you can see here, good numbers in recall and precision. And then our numbers provide clear evidence of strong classical performance, solid transformer performance, consistency across metrics. And we will scroll down to, on that note, our summary and integrated analysis. So, as we conclude, CodeSearchNet pipeline spanning retrieval, classification, transformer fine-tuning, and lab-style NLP analysis to provide coherent and end-to-end interpretation of system behavior and model performance. All metrics and findings derive directly from the executed notebook and represent the best performing version of this notebook. That's my disclaimer. I feel like I have to put that in there. Retrieval Performance Docstring Code Search. The character level TF-IDF retrieval model evaluates how effectively a natural language docstring can recover its corresponding code snippet from a large multi-language pool. The top retrieval metric score, MRR, at 10. 62, recall at 77, precision 77, and DCG at 65 interpretation. The recall at 10, precision at 10.78 means that nearly 4 out of 5 docstrings, the correct code appears within the top 10 retrieved candidates. The NDCG at 10 shows that relevant items tend to appear near the top, but not merely within the list. My conclusion is that character TF-IDF 3 to 5 grams is surprisingly strong for structural matching across Python, JavaScript, and Java code bases, and serves as a robust, lightweight baseline for code retrieval systems. Classification performance, to docstring, to language identification. This section compares classical TF-IDF machine learning models with a fine-tuned Dilbert transformer for inferring the implementation language, which would be Python, JavaScript, or Java, solely from the docstring text. Model performance comparison, model accuracy macro F1, Bayes, TF-IDF 1 to 2, is at 90, linear SVC is 91, and Dilbert is 91. Linear SVC emerged as the strongest classical baseline, consistent with empirical results in Lab 3 and 4. Dilbert, despite being trained from scratch on this dataset with a fresh classification head, closely matches linear SVC and provides deeper semantic generalization. Bayes performs well, but underfits more complicated linguistic cues compared to SVM and transformer models. My conclusion: Dilbert achieves performance that rivals or exceeds classical linear baselines, confirming that transformer-based architectures provide meaningful improvements when handling variety and subtlety in docstring phrasing. I felt that it was important to consistently integrate prior learning from labs and deliverables into the final project. Um, to integrate labs 1 through 8, we extended the notebook with additional analysis demonstrating that CodeSearchNet docstrings exhibit robust natural language properties. These analysis validate applying NLP techniques beyond simple classification or retrieval. And here's my key findings with that. Advanced normalization and lemmatization. Lab 1. Lemmatization reduces redundant inflected forms. Stopword pruning improves TF-IDF signal-to-noise ratio. Clean text retains high semantic fidelity. 2. Token distribution and Zipf's-law. That was Lab 2. Frequency rank plots follow zipping curves. This confirms that docstrings behave as natural language corpora, not arbitrary technical text. 3. Additional classical models plus hyperparameter tuning. This was included in labs 3 and 4. Logistic regression performs well, but is less stable than SVM. Grid search CV improves linear SVC performance and reproducibility. 4. Enhanced retrieval metrics. That's from lab 6. Error analysis highlights predictable failure modes, ambiguous docstrings, overloaded functions, and more. 5. NER, summarization, QA, rogue, lab 8. NER correctly identifies entities inside noisy technical docstrings. Summarization provides coherent, reduced representations. QA probes semantic structure, showing docstrings contain answerable content. Rogue scores quantify summary, context, overlap. The conclusion here is docstrings are linguistically rich. Therefore, they support a wide range of NLP tasks, reinforcing that CodeSearchNet is a suitable benchmark for both classical NLP methods and transformer-based models. Final project conclusions. Character-level TF-IDF is an extremely competitive baseline for docstring-to-code retrieval, consistently achieving strong MRR, recall at 10, and NDCG scores. This demonstrates that simple statistical features remain effective for structural text-to-code alignment. Linear SVC remains the strongest classical classifier, but Dilbert matches its performance while delivering better generalization and deeper semantic modeling, especially on noisy or multi-sentence docstrings. The lab 1 through 8 integrations, normalization, token analysis, retrieval metrics, NER, QA, summarization, rogue, they show that CodeSearchNet docstrings follow natural language distributions and can be analyzed with standard NLP pipelines, not just code-specific tools. The full pipeline, retrieval, classification, transformer training, and linguistic probing, represents a complete research-grade workflow. Section 8. Limitations and future work. Slide 11. This project has several limitations. Docstrings are noisy, incomplete, or inconsistent sometimes. TF-IDF is lexical and not semantic. Retrieval depends on top K ranking thresholds, and transformers truncate docstrings at max length. These inform recommendations for future iterations. Slide 12. Future work. You could train CodeBERT or GraphCodeBERT for code-aware embeddings. Maybe integrate AST structures via multi-model modeling. You could use ranking loss, fine-tuning for retrieval. You could just increase the data set by 10 times or 100 times or 1,000 times or a billion times depending on your compute power. Or you could explore contrastive learning for docstring code alignment. Capstone pipeline overview. What we did here, 1 through 6, is we loaded CodeSearchNet, hopefully through Hugging Face, but we had a fallback method there. We pre-processed docstrings with normalization, lemmatization, and code. We build TF-IDF and transformer-based features for retrieval and classification. We train classical models like linear SVC or regression, and we fine-tuned Dilbert with it. We evaluated retrieval metrics, the MMR or MMR, MRR, recall, precision, NDCG, and classification, which is accuracy in F1. And then we interpreted this behavior via error analysis and lab-style NLP tools with NER, summarization, QA, ZIP. Final summary and conclusion. And here are my final thoughts. This project, my project, demonstrates classical models like linear SVC remain extremely strong baselines. That character level TF-IDF is highly effective for code retrieval. Effectively, that Dilbert provides strong generalization and is well suited for scaling. That doc strings can indeed be treated as natural language, which enables powerful cross-domain NLP applications. And ultimately, that together, retrieval plus classification plus EDA plus generative NLP forms a comprehensive pipeline for Docstring-Aware code understanding. As we finish this off, we'll pivot back to this notebook over here and just look at some of these numbers. Here's your fine-tuning, the limitations, docstring quality. It all documents everything that I just said, which is why I thought it was important to have the notebook and the PowerPoint for this presentation. You can see the overview, the conclusion, the future work, and all of this. If you would like to ask any questions, feel free to email me or reach out. You can find me on LinkedIn, and that's it for now.